Okay, great. So today I'm going to talk about zeta functions and wave conjectures. So I'm going to start off with pointing out an error that I made, well, kind of an error that I made yesterday. So when we were talking about the degree of a divisor, I was like looking through my notes and I was like, when I was talking about hyperelliptic curves, I looked at this divisor, which was like you take a rational value of an FQ rational value of x, and then look at the square root, and I then called it a degree 4 divisor. And I was like, that just seems wrong. Like, morally, that's not the right thing for it to be. And if you try to compute compute some degree problems for divisors, right? So maybe you ran into some issues with this. And I apologize for that, but if you and let me say why this happens. So if you think about this over the algebraic closure, everything is fine, right? So if you're thinking about these points sitting in the algebraic closure and a divisor as the sum of these points, then you can just look at, so if so over I want to emphasize this. So over FQ bar, everything is fine, right? If you have D equal to a sum of points, right? So maybe I should NPP, right? Then you take the degree. Well, now you're over the algebraic closure, and then you just take it to be the sum of these NPs. Everything is, so things work out the way they should be. However, if you try to use just, if you try to directly say that, okay, over a fixed field FQ, if I do this, right? Oops, degree D equals NP times degree P over some FQ, you start running into weird problems, right? So this becomes a divisor of degree 4, not fun. Okay, so what you want to do here, and this sort of ties into the philosophy that sort of comes into play whenever you're talking about non-algebraically closed fields, is that primes are not points anymore, right? They're irreducibles, right? So they're irreducible elements. So for instance, over here, the fact that both of these are Galois conjugate, you want to take that into account somehow, right? So what you do is this sum of NP degree P, instead of summing this over all points, you collect all of these, all of the points that are in that are in the same Galois orbit, right? And then you somehow acknowledge the fact that, okay, so that they're in the same Galois orbit, and you count that whole orbit just once, right? So the sum should be over Galois orbits, right? And there it becomes very important that D is defined over the ground field, right? So if D is defined over the ground field, then you can talk about all of these Galois orbits, right? And then you can split up all of your points into Galois orbits, and then count each Galois orbit once, and then say, okay, I'm going to sum over NP degree P. So if D is defined over a particular field, then if you sort of work this out, you can directly think about this over the algebraic closure, right? So you can just use this particular definition, if you like, over the algebraic closure, right? So if you want to think about the degree of the divisor, and your divisor is defined over FQ, right? Either you can say, okay, what is the degree of this over the algebraic closure? Or you can say, okay, I'm going to take points, divide them into Galois orbits, and then use this definition of degree. Yeah. Okay. So that means that in particular that this is a degree 2 divisor, right? Because each of the points is defined over degree 2, but it's one single Galois orbit, right? So this is sum over, right? So P1 plus P2 is like the same thing, right? So it's a degree 2 divisor. There's no sum, sorry. So it is a degree 2 divisor. Right? And it's rational. Okay, so maybe I should take a few questions here, just in case there was some confusion. I don't know how far people got in my problems. I know I've overloaded the thing with exercises, I'm going to stop adding exercises now. So hopefully this didn't cause too much confusion. I think most people were fine, at least the people I talked to, but just in case. Okay. I don't see any questions. Okay, so we're gonna move on, right? So I've written down a more thorough example in Zulip, so you can check it out there, right? So it's a little more involved.
Soumya?
Yeah.
There is a question. What if the NP are not the same for all the points P in the Galois orbit? Somebody asked.
So that's a very good question. So what happens is if D is defined over the ground field, right? Then it turns out that all of these NPs have to be the same because the Galois action has to take one of the P's to one of the other ones that is like Galois conjugate to it. So the NPs are so if D is defined over FQ, then you're sort of forced to have all of the NPs for a particular Galois orbit be the same. That's a great observation. Awesome. Great. Okay. So today I'm going to talk about Jacobians, state modules, zeta functions, wave conjectures. Let's see how far we get. Okay. So recall, right? So recall that, oops. That Jacobians, right? Which were basically defined as pic naught, right? Of C. Here, I'm just, when I say pic naught, so this was degree 0 divisors over the principal divisors. And here, you can take, you have to be careful about which fields you're defining your divisors over, right? So if you take a degree 0, a degree 0 principal divisor over FQ, then it's going to be so if you take a principal divisor of a function that's defined over FQ, then the divisor itself is going to be defined over FQ, right? And so on and so forth. So this is like for every field and every field extension, there's like an inclusion. So and C K, right, is contained in div 0 K. So here I'm just keeping track of the fields, right, where K is some extension of FQ. And so so the Jacobians are this thing. In particular, they have a group structure, right? So it turns out that they're an example of what is called an abelian variety. But we won't worry about what that is. Just remember that the two key points are, first of all, the Jacobians are algebraic objects, right? So they're algebraic, which means in general, they're going to be defined by a bunch of equations. And the second is that they have a group structure, right? And that you can see by just adding together divisors. Oops, a group structure. Okay, awesome. And so what you can do is you can define, so you can define the n torsion, just as we define the n torsion of an elliptic curve, you can define the n torsion of a Jacobian, right? So this is, so you can take all of these, right? And this I'm going to look at all the FQ bar points. So Jacobian, so this is the notation for the n torsion, and its FQ bar points are all of those points inside the Jacobian, so all divisors that are defined not necessarily over the ground field, such that n times p equals 0. Right? So this is very similar to an elliptic curve, right? So you're just taking all of those points so that when you add it to itself n times, you get 0, right? Which is the trivial divisor. Okay, great. So again, if so it turns out that if n and p are co-prime, then the n torsion of the Jacobian, I'm going to start omitting this thing just for convenience. This is isomorphic to z mod nz to the 2g, where g is the genus of the curve. Right? Okay. So now, if you're over a finite field, or well, if you're over a field of characteristic p, so just as in the elliptic curve case, we had so recall that we had the action of Frobenius on an elliptic curve, right? So we said that if E was defined over FQ, then this EQ would be equal to E, and then you would have this map, XY maps to X to the Q, Y to the Q, right? And so you can do the same thing with the general curve, right? You can just take C and then it's defined over FQ, so you do this, and then you take XY, and then you map it to X to the Q, Y to the Q. This is prob Q, right? Of course, you can also define prob P, right? So, well, this is assuming C is a plane curve. In general, if it's not defined by a plane equation, maybe you need to add more variables, but basically take each of your coordinates and raise it to the qth power, right? So prob P is going to be denoted by, is going to denote this following map, right? So this is X, Y, maps to X to the P, Y to the P. And so just as in the elliptic curve case, you get an action of prob Q on the n torsion points of the Jacobian, right? Because as we said, you can have the Frobenius acting on the divisors by acting on each of the points, right? So you get so on each divisor you get the action of prob Q, and then you on the n torsion you also get an action on the n torsion of the Jacobian, right? And how do we define the Tate module? Well, we do the same thing that we did before. Now I'm going to call it TLC. I'm going to take the inverse limit of the z mod n to the 2g's. So of Jacobian, so L is a prime that's not equal to P, right? And I'm going to take Jacobian, and I'm going to take the, oops. I'm going to take the L to the n torsion of the Jacobian, and then take the inverse limit over n, right? And so similar to the elliptic curve situation, right? So you get an action of Frobenius on this. Right? And this is isomorphic to ZL squared. Sorry, not squared, to the 2g, right? Because each of these is isomorphic to Z mod L to the n to the 2g. So you get a Frobenius action on this Z mod ZL to the 2g. And so what you end up with is, so you can think of Frobenius as a 2g cross 2g matrix. Right? So again, just as in the elliptic curve case, where you had a 2 by 2 matrix, right? Here you've again linearized your problem by thinking of this as a 2g cross 2g matrix. Okay. Any questions about this? Okay. So as before, well, it's a matrix, so now you can study its characteristic polynomial, right? So we're going to denote it in this way. So the characteristic polynomial is given by PCQX, right? And I'm not going to write it out, but this is a degree 2G polynomial, right? I'm going to write it as a product of x minus alpha I going from 1 to 2G, right? And so these alpha i's are the eigenvalues of Frobenius. Eigenvalues Frobenius. All right. So if you remember the elliptic curve case, then what I say next is not going to come to as much of a shock to you, but it's a pretty cool fact that this is actually a polynomial with integer coefficients and doesn't depend on L. Right? So what we're going to do, right? So is now we're going to study this polynomial and see what it gives us.
Soumya? There are a couple of questions. One is the definition you wrote for Jacobians makes it clear it is a group, but can you talk about the structure it has that makes it into a variety?
Ooh, this is it's a great question, but it's a I think it's too long to talk about it right now. So
Yeah.
so it's not something that has a short answer. It's a non-trivial fact that it is a variety, right? That it's defined with equations. So what I can do is maybe later when I'm like doing a BBCU, so when I'm in BBCU, maybe you can come talk to me about this.
Okay, that sounds good. Yeah, another question is, in order for Frobenius Q, the Qth Frobenius to act on the n torsion of the Jacobian, are you assuming that C is equal to its Frobenius twist, CQ?
Right, yes. So C is defined over F cubed, that's correct, sorry. Maybe I should say that more clearly. So here we're just taking the curve to be defined over F cubed. That's what we get in our case.
Okay, there's actually one more. Is there a name for that variety group? Just in case I can't come to this later discussion, I wanted to read about it. What's called the variety?
It's called the Jacobian variety. Oh, and it's an example of an abelian variety.
Yep.
So, an abelian variety. So, actually, so there's a reference. So the reference for abelian varieties in general. So maybe this is not. If you want to go into a lot of into detail about this, is these notes by Milne. So he has this notes. He has these notes on abelian varieties on his website. And that's like the classical, at least like for me, that's the go-to place to learn about abelian varieties if you want to go into detail. Yeah, some great questions. Okay, so right, so okay, so next what we're going to do is we're going to see. So remember that, well, C is some curve over FQ. And so you can talk about points on this curve that are defined over FQ to the n, right? So what we want to see is what this Frobenius polynomial, so it turns out that this Frobenius polynomial is related to this somehow. And what we're going to do next is examine this relation, right? And so we're going to see how knowing this can give you exactly how many points you have over each extension, actually, right? So to start off, I'm going to define something called the zeta function of a curve. And the way it's defined is it's a generating series, right? So it's defined as the following. You take the CT to be, you take the exponential of the following sum, bigger than or equal to 1. You take the FQ to the n points of C, with them in a generating series of this form, take the exponential. Awesome. I'll let you stare at this for a moment. Right. So let's do some examples, right? So let's take C equal to A1, right? So A1 has Q to the n points over FQ to the n, right? So it's just a line. And so this is all over, so A1 over FQ. And so what Z A1T is that it's the exponential of sum over n bigger than or equal to 1, Q to the n, T to the n over n. And okay, so to simplify this, right, I'm going to remind you what the power series expansion of log is, right? So log of 1 minus x, right? So negative log 1 minus x is x plus x squared over 2 plus x cubed over 3, x to the fourth over 4, blah, 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 blah. So this whole thing is just the exponential, the negative of log of 1 minus qt, right? So therefore, ZA1T is 1 over 1 minus qt, right? Now, let's do another example. C equal to P1, right? Let's take a projective curve. This has, so over FQ to the n, it has Q to the n points coming from the A1, and then there's a point at infinity. So there's one more point, right? So C FQ to the n. Great. And so what this gives you is the following. So it gives you that Z of P1T is the exponential of the sum. So there's a Q to the n, T to the n over n, and then the one sort of lives by itself. And so if you use the log identity again, what you see is that this is going to be 1 over 1 minus t times 1 minus qt, right? And so it's a modification of this one. That's not a coincidence. Awesome. So in both of these cases, ZCT turned out to be a rational function, right? And a very nice looking function. And somehow this packages all of the information about the points over each extension, right? Okay. So maybe I'll say a little bit about why this is called the zeta function, right? So recall, so if you have the Riemann zeta function, right? So this is the famous one, which is the sum over 1 over n to the s and bigger than or equal to 1, right? And there's like so many conjectures about where its zeros are, blah, blah, blah. Notice that if you want to write this out, you can, what you can do is you can take zeta s and you can factor it as 1 over 1 minus p to the s, right? But it's the negative 1 over p, all the primes, right? And another observation that I can make is that p is the size of p. This seems like a dumb observation to make, but this is going to be useful, in that you want to do the same thing with function fields, right? So you want to do the same thing with curves. So you can define zeta c. So c is a curve over fq. You can define zeta cs as the following. Well, you're going to take x inside c, right? You're going to take points. You're going to take a product over these points of 1 minus q to the negative degree x s, the negative 1. Okay. And so an exercise So you have to be a little careful about what you mean by a point here. Again, if you're not over an algebraically closed field, remember that a point, you have to be a little bit careful. But right, so you have to be careful about how many times you count the point, basically. So the exercise is to show that z c q to the negative s is zeta c s. Great. So this is why this is called, well, this is one of the reasons it's called a zeta function, right? And this is very similar to this because q to the degree of x, right, is the size of the field that x is defined over, right? So that's why that's one way of looking at these things. Okay. And so now I'm going to state one of the major theorems in this area. So these are called, so this is a theorem now, well, since the 70s. So I'm going to call, actually, so these are called the Way conjectures, but they have been proved for some cases. So I will say that there's a general version, so general version that was proved by Deligne for, well, by Deligne, Grothendieck, Dwork, and a lot of people. So for varieties, right? So smooth projective varieties over FQ, right? So this exists, but I'm not going to state it. Right? Today we're only going to do the version for curves. And the reason I mentioned this statement is that a lot of beautiful theory in math was actually developed in order to prove the general version. So like all of Lefschetz's theory, for instance, was developed to answer the way to prove the Way conjectures. Right. So today we're just going to talk about the version for curves. Right. So the theorem has three parts. Right. So C again is a smooth projective curve over FQ. The first part is called rationality. So, and that says that the zeta function is actually a rational function. And so ZCT is the product over 1 minus alpha IT over 1 minus t times 1 minus qt, where I goes from 1 to 2g. And these alpha i's are nothing but the Frobenius eigenvalues that we saw. Eigenvalues. Okay, I don't know. So this is very cool, right? The second is called the functional equation, which tells you about a sort of symmetry in the zeta function. So this is qt inverse equals q to the 1 minus g, t to the 2 minus 2g, zct. This is very useful. And here g is the genus of the curve, right? G. And the third is something called the Riemann hypothesis. And this was like the hardest part in the proof, and was proved proved last.
So yeah.
Yeah.
I have a question. I don't know if your notes have some sort of like notes about how to compute these things in Sage or Magma. I can do that in my course or in my notes if you want to.
Yeah, sure. So I put in some exercises which involve computing the zeta function or the Frobenius polynomial for curves, for certain curves. Is that what you're talking about?
Yeah. So I can explain. I'll quickly explain how to compute a zeta function for a curve or a finite field tomorrow to start with as an example, something to do in Magma. There is also a question. This is a very important question. Somebody asked, I thought the Riemann hypothesis was still unproven. Did you prove it, Soumya?
Yes, I did. No, I'm kidding. This is so okay. Maybe I'll come to that in a minute, right? So let me just finish the statement, and then I'll say what it means, why this is something. Okay, so alpha I, so the absolute value of these alpha i's is q to the 1/2, where this denotes the complex norm. Right, so these are all algebraic integers because Frobenius is an integral polynomial. So this is the complex norm. And so one of the reasons this is called the Riemann hypothesis is because, so remember that for us, alpha i's, right? So ZCQ to the negative s was zeta CS, right? So ZCQ to the negative 1/2 is zeta C 1/2, right? And so alpha i's, right, were zeros of Frobenius, right? The Frobenius polynomial. So 1 over alpha I because of the way ZCT looks, right? So if you look at the expression for ZCT, so 1 over alpha I is a zero of ZCT, ZCT, 0 of Z. And so what this tells you is that all of the zeros of zeta CS, right, lie on the line s equals 1/2, which is why this is called the Riemann hypothesis. And so to answer the question, what this is called is the Riemann hypothesis for function fields. And this is known. Maybe what you're thinking of is the Riemann hypothesis for number fields or for Q. So the Riemann hypothesis for Q, right, which is about the Riemann zeta function that I wrote out earlier, right, that is not proved. That's still a millennium problem, right? And so this is actually a very interesting, okay, so I'm going to philosophize for a minute more. So this is actually an important thing. So what happens is a lot of theorems that you see in life, there will be two versions, one for number fields and one for function fields, right? And so sometimes, in a lot of cases, not all cases, but in a lot of cases, the version for function fields you will find has been proved while the version for number fields hasn't. And the reason for that is that the function fields version, right, gives us access to algebraic geometry, right? So you can use geometric objects, right? Here you're using the fact that these are curves or varieties, right? And so this have access to geometry, right? So this is an example of one of those classical theorems that's been proven for the function field case, but not for the number field case, right? So not claiming to have the Riemann hypothesis. That'd be cool though. Awesome, great question. Okay. So, okay. So there's a couple of observations that you can make about the roots of Frobenius of Frobenius polynomial, but maybe I'm going to skip over that because of the lack of time. But the cool thing, there's a couple of things that we're going to show. The first one, right, is that, so this is the first corollary, is how do I use this to count points, right? So C of fq to the n, right? So remember alpha i's are eigenvalues of Frobenius q, right? So eigenvalues of PCQ, x, right? So this is given by q to the n plus 1 minus the sum over alpha I to the 2g. Right? So you get an exact formula. So if you know the Frobenius polynomial, then you can count the number of points over every eccentric. Right? So often actually, since Alvaro is going to do this tomorrow, the way computers sometimes calculate Frobenius polynomials is by going the opposite way. Right? They count points on curves because those are like things given by equations, and then they use that to calculate the Frobenius polynomial. So you can go either way. Right? And so the second corollary, so this one actually, so this is not very, maybe I'll say a word about the proof. This is not very hard. You can actually just so remember that ZCT, right, was exponential of the sum over these things, to the n, t to the n over n. So if you take logs on both sides, so if you use the rationality of the zeta function and then take logs on both sides, you get that the sum over c fq to the n t to the n over n, right? This is sum of the logs of 1 minus alpha I t's, right? Over, nope, minus, my bad, minus log of 1 minus qt. Awesome. Right? And then if you use the power series expansion for logs and then compare the terms, the coefficients of t to the n, then you'll get this expansion. Right? It's not that bad. Awesome. The second corollary, which is a corollary of the Riemann hypothesis and of this and of corollary 1, this is called the Hasse wave bound. And if you recall, we talked about this for elliptic curves. This is a version for a general genus G curve. And that says that if you look at the number of FQ points of C, so you can also do Q to the N. So C is over FQ, right? So minus Q minus 1, right? That this is less than or equal to 2G times square root of Q, right? So remember, for elliptic curves, we said that the AQs, right, which is this quantity for elliptic curves, were less than or equal to 2 square root Q. This is a higher genus version, right, of the Hasse bound. And how does this, so the proof for this, right, is not, so if you know the Riemann hypothesis, which is a big thing in itself, this is actually equivalent to the Riemann hypothesis, right? So the way this goes, with size here, is that you notice that the alpha i's, right, these all have complex norm 1/2, right? So and so from sorry, way to write this. And so if you look at the sum over alpha I 1 to 2g, right, the absolute value of this is less than or equal to 2g times square root of q, right? So if you use this, so this is from the Riemann hypothesis. And if you use this, then you get exactly this bound, right? So if you use this plus corollary 1 implies corollary 2. Okay. So what this gives you, right? So even in the notes, for instance, there's a couple of more bounds on the number of points on this curve. And maybe you're wondering, okay, why care? Like, why do I want curves and why do I want points on curves? So for example, one of the things where these things come up is in coding theory. So people in coding theory like curves which have a lot of points, right? So it helps them make larger codes and like have more leeway. And so an example of, so they're always looking for examples of curves that achieve this bound, right? And so yeah. So I think I'll stop there because I'm out of time. But if there are any questions, I'm happy to answer them.